Good morning, ladies and gentlemen. My name is Srikanth Maru. I work at Cricket as a Senior Manager, Data Engineering. And before that, I worked with various Fortune 500 organizations, and I've also worked with startups, specifically around the data platform and its architecture. Now, we've been to most of the talks in here, which are very focused on AI applications, ML applications, and even the previous talk, which emphasized mostly on MCV servers. The fundamental aspect that I wanted to cover today is to be able to build successful AI and ML applications, there is a prerequisite in terms of data platform and its architecture, which is the crux of building any successful AI applications on top of that. Now, specifically in building AI platform and its infrastructure, there is certain kind of architectures which have trade-offs in terms of the speed, the accuracy, the completeness. So what I'm going to cover today is targeted around Lambda architecture, and we're going to dwell into the details about how it can actually help AI or ML applications build on top of this architecture be successful. And one thing I would like to clear out before I start is I've met few people yesterday when understanding about what they're doing and talks that they're giving. And when I mentioned the Lambda architecture, most of the people related it with AWS Lambdas actually. So it is not about AWS Lambdas, it's mostly about the architecture components on what the Lambda specifically provide. It's nothing to do with the AWS Lambdas in here. Now, let's talk about the problem statement before we understand why these architectures are very essential. If you talk about AI projects failures in general, 80% of these projects fail to deliver business value, not because we don't have sophistication in the machine learning models, or we don't have expertise in building, or the data science expertise. It's predominantly related to three main categories, and it is from the Gartner's research. The first element that contributes to failure of AI projects is poor data quality. If the models are trained in bad inputs, you get unreliable outputs. It's as simple as garbage in, garbage out, actually. So I've worked with many recommendation systems where the models that are trained very well in lower environments, when they hit the production scale, they tend to really deviate because the quality is not appropriate to the mark actually, right? Now, lack of scalability. So as it says, solutions that really work when we do proof of concepts or in development environments, and we get pretty excited when we look at the outcomes that we identify in these lower environments. But then when you deploy it into production scale, you're talking about petabytes and terabyte scale informations, and it's hard to scale these platforms because you do not have unlimited amount of resources to be able to run these AI applications. And the third element is real-time features. In the given world where the given information is becoming very stale in a very lower frequency, it's important that the platforms that you're building, the data platform and its infrastructure that you're building, supports the real-time nature. So these three factors, we're going to dwell how the Lambda architecture is going to make sure it actually tackles all these scenarios and more than these problem statements. Now, before we understand more about Lambda architecture, it's only fair to talk about what a general data pipeline is. So people that doesn't come from a data background, imagine this as a workflow of components, a workflow which has like sequence of steps. So you talk about data ingestion, where you collect real-time data, batch-oriented data, scheduled at different frequencies, hourlies, nightlies, or even at sub-millisecond latencies. So you have your ingestion component, and next comes your data processing. Data processing is where majority of the business logic exploration and business logic implementation, metric development happens in this data processing layer. Storage is where it provides the downstream applications in terms of faster access. For example, there are file formats like Avros and Parquet, which helps you run column-oriented databases or understand the schema drift that happens within your data. And serving, how do you serve your data that's stored in your data platform? So data engineering or data platform, if you see, it's more of an horizontal that actually supports multiple pillars. So you talk about BI being one of the use cases, machine learning models being one of the other use cases, AI applications, and any front-end systems that's actually built on top of these platform components. So serving is majority based on either REST API based data serves or inferring these data platform components through models. Now, from the Lambda architecture components, So the reason why the Lambda architecture requirement is necessary is fundamentally there is a tension when building the AI applications. The tension happens because for training, you need complete and accurate data, and that's where you'll be able to generate good experiences. But for inference, you need more current or fresh data sets. So they don't really go well with it. So at one time, you're saying you need complete and accuracy data. In another aspect, you're looking at fresh and more current information, actually. There is usually a trade-off, and you're only asked to choose between one of these architectures, because none of the existing components really go well with both these trade-offs in a way. So what we're going to talk is, in the Lambda architecture, the architecture supports both these, try to at least address both these use cases, where it can handle the completeness and accuracy, as well as the low latency aspects of it as well. And the way it handles is, it has three main layers. So we talk about a batch layer, a speed layer, and a serving layer. So batch layer is where the focus is mainly on completeness and accuracy. You're looking at an hourly pipeline or a daily pipeline and running at different cadences. And you can run more compute-intensive logics because it has its own resource availabilities to be able to execute and deliver that content. Speed layer is looking at answering specific points. You're not looking at answering volumetric use cases, but you're addressing specific to the point use cases, and that's where the low latency use cases are much better. Serving layer, oftentimes, if you don't follow these sort of an architectures, what happens is you end up building different serving layers for your batch environment, different serving layers for your real-time environment, and becomes very cumbersome to maintain for downstream applications how these information can be incorporated. So you're looking at, let's say there's an LLM model that's looking at receiving this data. So it needs to have separate code bases, separate maintenance for speed layers. It needs to have separate unified schemas for batch layers as well. So this try to eliminate that problem by actually centralizing the schema maintenance. Now, batch layer. So as we touched briefly on it, so what we're looking at in batch layer is historical storage. Not every use case that we have in AI needs to be dependent only on the most recent data. So there are many use cases where you depend on historical information. Look at any recommendation system that you see in e-commerce per se. They don't look at the most recent information, but they look at all the historical trends, the clustering of the users, to be able to identify how well we can serve you better. Batch pipelines. So it is also not about how well you can receive the data, but more importantly about having the ability to receive these informations at definite frequencies. There are upstream systems that are capable of giving you the data in a more in a definite frequency, like hourly jobs, weekly executions, or daily executions. But the main focus in these pipelines is not the rate at which you can actually process this information and deliver the content. It's more about the completeness and accuracy. You get more benefit in terms of delivering accurate content to your LLMs and your models when you focus on these batch-oriented pipelines. Curated features, what it talks about mainly is, if you look at a BI application, BI applications have very sophisticated metric definitions and logics, which are very compute intensive, and they cannot be run in a definite scale in a real-time window. So that's where the batch layer focuses on giving you that ability. The reason why the accuracy is guaranteed is you have all the time in the world to be able to build these contents and all the resources that are available in your cluster to be able to give you more accurate information. So the streaming layer. So what this speed layer focuses on is the kind of attributes or the kind of questions the speed layer tries to answer are very definite. What it means is it is to the point actually. They're not very wide, but they're very narrowed and to the point. Similar to batch layer, where you have an ingestion component, where you have a data transformation layer and a service layer. In the speed layer, you have a streaming component where you have high throughput data ingestions that are happening in petabyte scale. And similar to batch layer, where you run your transformations in a large scale environment, although you don't have the luxury of running these aggregations in the speed layer, you still have the ability to do windowing. So the window environment is only to a specific interval, within that stream. You can run deduplication logics. You can still run certain validations in it, but they're very narrowed and well defined in a way. And the kind of, the length of your windows determines how fast your LLMs can actually get the most recent information. Feature stores. So feature stores are very essential because the context of a given user constantly keeps changing in this world. So unless and until your feature stores are up to date with the most recent information, otherwise you're looking at stale predictions and stale outputs to be generated to your LLMs. Now, serving layer. So in most of these architectures, so they tend to introduce more complexity because you have your batch layer and your speed layer, and the receiving layers, which are like downstream applications. They tend to handle these two things independently because they don't share the unified schemas in a way. But using this architecture, what it actually talks about is you don't have to maintain two separate or inconsistent schemas, but you can maintain unified or centralized schema across these layers so that the application doesn't have to really worry about whether I'm processing the high latency data or low latency information. So it's more a centralized schema that it can maintain. So that's where you serve the online applications and offline applications because they tend to meet both the use cases. And the reason why you have consistent schemas in here is it is a centralized architecture that defines a single schema for both your batch data sets and real-time data sets. Now, once you have this architecture in place, this is just a depiction to show how the reconciliation actually looks like. So in the speed layer, you focus on collecting as much information as possible that's available at a low level latency actually, right? And you get this information, put it into your databases, be it a Redis cache or a Cassandra database or any other document-oriented DBs or key value stores where the fast layers can start consuming this data. Now, in the second processing, what batch layer does is it has its own time, it has its own resources to be able to get the data, and this is where you have the luxury of running a good amount of data quality checks to identify if there's any anomalies within the data, and also go back and correct the same entries which are made by your speed layer. So you're trying to improve the accuracy that's actually done by your speed layers. So if the model is looking for more recent information, they're already being served because you have the information that's done by the fast layer. And what it does with the batch layer is it's more eventual accuracy. So you get your data more updated and to the correctness of the information based on the next update that it happens with the result reconciliation. And unified serving, so what it's talking about is you don't have to maintain different schema structures across so that the LLMs doesn't have to change or the downstream applications doesn't have to keep worrying about whether I'm serving the same content or do I have to look for a different schemas since the layer has changed. Now, in the Lambda architecture, the data quality and governance. In the Lambda architecture, you have the luxury to be able to run a good amount of data validations. There are many frameworks that are available in the market, open source and commercial, which is like, for example, Great Expectations is one of the packages that's out there. DQ is one of the libraries where asynchronously and synchronously, you can plug it in both to the batch layer or to the speed layer to be able to run your data validation checks. And schema registry, when a data set, a raw ingestion data set is identified, you define the schema at a single point itself. If there are any updates to the schema registry, you keep maintaining those versions within that registry itself so that irrespective of batch or speed layers, it doesn't have to vary. Lineage and catalog. Across the organization, it's not just the data team that's actually reliant on these attributes. The whole organization needs to understand what these data sets are, how the lineage actually expands, and given attribute in the given metric, how does it update and where is the upstream information available to us. So the lineage and catalog that's available in this Lambda architecture gives the whole organization the ability to be able to look at the overall workflow implementation within the data team. So Prometheus-based alert, this is something that we use in our organization as well, where you can plug it in or start collecting these metrics into Prometheus-based alerting systems, and you can have unified alerting systems across your batch and speed layers as well. So there are several opportunities that are available within this architecture to be able to tune this application. First thing, windowing and triggers. So windowing is for the speed layer. The size of the window definition controls how much of a low latency or a high latency that you can expect within your speed layer. So the lower the window size, the faster you get the throughput, and the downstream applications will be able to consume this information much faster. But at the same time, there is a trade-off. The lower the window size, let's say if you're expecting too much of a duplicate information that needs to process in your system, you're unnecessarily crunching the duplicate information if the windowing size is lower. Triggers are more for batch layer. So trigger is more of a cron tab execution or a dependency based execution, where it tells you, depending on the availability of the data from the source, do I need to schedule it at 15-minute intervals? Do I need to go with nightly batches, or do I need to go with hourly batches? So you get the ability to be able to control what sort of a trigger that I would need to run my pipeline. Across these layers, you have opportunities to do JVM-based tuning, mostly for memory allocation and garbage collection triggers. And parallelization. So the reason why parallelization is more important is, as I said, you do not have unlimited resources in any platform, data platform or infrastructure to be able to run petabyte scale information. So the way you actually sparse your schedule for these pipelines to be running and how well you orchestrate them, depending on how long is it going to, because there are data science pipelines that take more than 24 hours also to be able to crunch these numbers and give you outputs, because you're processing last 5 years, last 10 years worth of information to be able to generate the metrics that you would want. So parallelism, especially in the batch environment, gives you the ability to be able to play around this resource management. Serialization. So there are a lot of file formats that are available out there: Avros, Parquets, ORCs, even simple CSVs, JSON. So the serialization trade-off here is, for fast layers where you would want to avoid drifting schemas, you would want to pick something like Avro. But for batch-oriented executions where you would need more human-readable information, you can go with some binary formats or JSON-based schema structures. Although they involve more resource utilization, still human-readable, and it will be able to solve the problem that you would have. Observability and debugging. So this, in a data platform and architecture, a very common pattern that we see where you do not have complete visibility to what's happening in your ecosystem. Let's say there might be some data sets which might be serving stale data sets, and you wouldn't have any knowledge of it unless and until you have specific observability tools or monitoring tools that are put in place. So for example, data freshness is a very key aspects in the data platform, and there are days these things get unnoticed if you don't have the exact observability tools that are put in place, right? Structured logging. So across these layers, you would want to have one specific framework or tool that understands the logging mechanism, unified logging mechanism, and it would be able to understand this information. So typically you go with JSON-based logging structures where you don't have to implement complex observability or debugging tools to be able to understand this information. Pipeline metrics. Pipeline metrics here doesn't talk about the KPIs or business functionalities. It talks more about the batch IDs. Like, let's say every given execution that you have in a workflow or a pipeline needs to have a correlation batch ID, so that you track how the information is flowing through even within your platform. So how do you incorporate these things? Canary-based deployments. So often it's very difficult in a data platform environment to have rollback strategies. Unlike the software world, when you update a table or alter a table and go with the table definition updates, it's not easy to revert them back. But still, how do we manage based on canary deployments to be able to have that rollback capabilities, and also understand the impact that these deployments might have before it hits production and creates greater impact. Now, simple best practices. Although the CI/CD integration is very common in the recent implementations, the data platforms or its infrastructure is still not in a very mature state to be, especially with the CDs actually. So continuous integration is still available, but continuous deployment is not so easier to be able to implement. But again, how do you get into that notion, at least to have that mindset to be able to deploy even in the data platform, is something that we would strive for. Infrastructure as code. I think most of the data teams that I've worked with and we have seen start with one monolithic architecture actually, and only after the initial phases, only when they start getting into this growth phase, people would realize, okay, we need lower environments, we need production grade environments, and we need it as infrastructure as code, so that you're not really asking for admin level accesses to be able to spin up one single EC2 machine or run some instances on the production environment. Now, data governance, I think we touched briefly upon it, and how you would actually give control of the data, of the catalog information and the lineage information that's available within your organization, not just for the data team, but to be consumable across the organization. Again, any data team, I think it's important for us to be able to start with data as a service sort of a mindset, so that you're not building it just for your internal consumption or internal KPIs or metric generation, but to be able to serve the pillars that are dependent on the data engineering, which is BIs or any ML applications. Today it's AI, and it could be something else for tomorrow. Now, business impact. I think we do go through these discussions day in, day out with the businesses purely because of the trust issues on the data actually. So reliable data sets. So how the Lambda architecture really focuses on not having multiple schemas to be maintained across batch and speed layers, having a unified structure across this environment, so that you will be able to identify the drifting schemas upfront and then not really wait for them to impact your production systems. Faster deployments, because you're not looking at having to maintain two different code bases or code structures for speed and fast layers, having to consolidate these environments so that the deployments could be faster. And cost savings, not really the attribute of a Lambda architecture, because you're still not going with a single layer, but you're getting the benefit of maintaining the two layers, having the batch layer controlling the correctness and the accuracy, and the fast layer focusing more on the low latency. It's still more expensive, but it is at the benefit of the business use case, I would say. So the checklist, I think from a data platform and architecture point of view, you're looking at the batch layer, which is focused on completeness and accuracy, the speed layer, which is mainly focused on giving you low latency data inputs, serving layer, which focuses on unified schema that needs to have across this environment, governance, which gives you data lineage and catalog, not just for the data team, but across the organization, and data validations is it's just not from the speed layer or the batch layer perspective, but giving you the ability to be able to plug in this synchronous and asynchronous validations to understand the quality of the data that you're serving downstream as well. And DevOps, to be able to go with continuous integrations, canary-based deployments, and having the observability and debugging mechanisms that you need to have in place. I think that's all for my talk. Thank you so much for your time.